Okay, trees. There's a lot of benefits to trees. We now give stormwater management credit for trees, for both retained and newly planted trees. We now have a new BMP, T516. If we're going to give credit for trees for stormwater management, how do we properly design for trees? If you're a landscape architect, you are well aware how difficult it is to get trees into an urban environment. There's a lot of competition for that space. And so how do we properly install trees so we get that benefit for long term? I mean, these are all pretty well documented. Energy conservation, air quality, carbon sequestration, aesthetics, increased property value, and now stormwater flow reduction. The number one issue with trees in the urban environment is providing enough soil volume. The soil that we put plant trees in is of very poor quality, and/or there isn't enough volume for a healthy tree. So you need a good upfront assessment. That can be through some borings or pits that could go along with your assessment that you're going to do for bioretention. Storage for stormwater dependent on the volume and type of soil. And understand your underlying soils. Preventing compaction is critical. A benefit is if you increase your soil volume to the amount that tree is really going to require, you're also increasing your storage volume for stormwater. So there's two pluses. There's a lot of competition and often very challenging. So here are the 4 rules of trees and stormwater management. They are solidly established. Larger mature trees provide more stormwater benefits than small trees. Evergreen trees provide more stormwater benefit than deciduous trees. Why? Water sticks to needles, that's right. Great for interception. Great for interception and then evaporation. Adequate soil volume and quality are critical for healthy, long-lived trees. So this is usually how we kill trees in the urban environment, not enough soil volume. Proper drainage design is critical. Too much water could kill a tree faster than too little. Isn't this a great picture? Available above ground growing space, that's a critical piece. Of course, utilities. Sight lines are critical, just like with bioretention, right? Correct plant in the right place. Same with trees. Considerations and location for type of trees, kind of continuing that. Below ground root space and ground level planning. Proximity to pave areas is critical for getting your stormwater credits. To get credit for using trees, your tree has to be in proximity to the impervious area that you're going to mitigate. So the test question right now is how close does it have to be? What's the metric? How do you measure? The tree has to be within 20 feet of that impervious surface that you're mitigating. You measure the 20 feet from the center of the trunk. The methodology here is to reduce that adjacent impervious surface by some percentage of the tree canopy. And that depends on whether it's evergreen or deciduous. Its location to pavement, not only important for the health of the tree, but also for your credit. You need to consider availability, obviously, soil and water, sun, wind, the maintenance, shade, all those things. Just like all of the practices we talk about, important upfront assessment. This is also a great picture from Seattle of some old trees, and the trees need to have some space. So trees versus concrete, who wins? Trees. They are powerful forces. You need to give them some space, and the trunk flare and roots can get quite large. Of course, you want to plant in the best appropriate places. High quality soil and volume is critical. Using pervious pavement for hard surfaces around trees can help a lot with that exchange of air and water and preventing the roots from uplifting the cracking sidewalks and roadways. So that's another strategy to consider. There's going to need to likely be some protection from surrounding activities, whether that's maintenance of utilities or whatever. So this is a picture of a project in the northern part of Seattle. It's a silva installation. We'll talk more use this as an example as we go through here. We've talked about all those other benefits, and now we're going to focus on stormwater management. So if you have adequate separation to your seasonal high groundwater, not bringing water in from somewhere else, you likely don't need under drain system. This is all predicated on good upfront assessment. If you are directing flow to that tree area, then you have to have very careful assessment of that soils, the tree species, and likely an underdrain system. When you're directing water to that tree from adjacent impervious surfaces, now you're getting into a more engineered system. Generally, the planting pit above the rooting zone That's 18, 24 inches should drain down within 48 hours. You can kill a tree quickly with too much water. If underdrains are used, incorporate an accessible control structure. In these systems, in bioretention, even permeable pavement, it's a great idea if you have underdrain systems to be able to access those underdrains, to be able to manage them. Cheap way to be able to monitor the performance of your system and optimize it if needed. Picture of the Silva-Cell system here, and it is a tree growing system that also can be used for stormwater management. General use level designation for Washington, that's not exactly correct. You might want to make a note or scratch that. It really is an equivalency designation. They're equivalent to bioretention if you use bioretention soil media, or you go through the technical equivalency process to show that the media you're using in that Silva-Cell is technically equivalent to the currently recommended bioretention media. Does that make sense? It's kind of a little bit of a gray area. It doesn't technically have a gold designation. It's really equivalent to bioretention. So, but it is a tree management system that importantly has that designation in Washington. So this project is very cool in that they have, in a very dense commercial setting, using the Silva-Cell, they're incorporating trees and bioretention and permeable pavement and connecting them all. This is what the structure looks like going in. They're basically just stacked plastic towers kind of that create a box, and you can fill that with soil, and so the trees have access to all that, to that soil volume, while at the same time you have a structural system that you can certainly walk on and drive on. Okay, reducing soil compaction. So this is probably the number one way you can kill existing trees during construction, but critical to clearly mark these areas if you're preserving trees. Critical to talk to your construction crew so they understand your objectives. Robust fencing. Your silt fence has little chance. If you think that'll work, likely not. I would say, certainly the chain link, and even chain link with the bright orange stuff all over it is much better. You need robust fencing. If access is unavoidable, there are some rules you can follow to hopefully preserve those trees. For foot access, 6 inches of arborist wood chips. That's your easier scenario. Of course, vehicle access is going to be much more challenging. 1-inch steel plate or 4-inch thick timbers over 2 or 3 inches of arborist wood chips. If there's no choice, you got to access, you got to protect those roots. The roots that are important for transfer of water and nutrients to the tree are located they're very shallow in the surface of the ground. So if you compact soil 6 inch deep, you're likely going to have significant impact on that tree. Post-construction, mulching is important. Planting bed with 2 to 4 inches of arborist wood chips. Sometimes you'll see the wood chips sort of piled up against the tree trunk. That's not recommended. Should be held back an inch or so from the trunk and replenish that. That's an organic material that will decompose and provide nutrient to that tree. Barriers. This is a big one. You can see 2 pictures here. Up top, they did a good job with the trees there, it appears, at least above ground. It's hard to know what's going on below ground, but that's a great setup as far as tree protection in an urban environment. Good space, air-water exchange, room for that tree to grow, at least apparently on the surface, and a low barrier there for protecting against pedestrians. In contrast, below the typical tree grate, a great way to strangle a tree to death if you don't change them out, if you don't expand the opening as the tree expands. And this is a great picture of how you can kill a tree or seriously restrict its growth with the tree grate. So these are really, of course, often used, very popular, but they're not the best way to protect a tree in the built environment. Existing trees, protection or mitigation from construction, well, there are several. Mechanical fixes for compaction. This is, now you're getting to the world of an arborist. If you have compaction, you have trees you want to preserve, and you've experienced compaction, you think that's going to impact the health of those trees, this is, you're calling in an arborist. You should have actually had an arborist in from the very beginning. But at any rate, the arborists are the folks who can consult with you on methods to reduce the compaction or soil density around that tree. And there are air spades, water spades, there are different kinds of boring configurations and ways to sort of reduce the density in that soil. Soil amendments, compost, and other biological products as well for improving the health of the soil if there's been construction damage. Tree root protection zone, that is a important concept for figuring out how much space a tree needs. It's a radial distance, meter or feet. This is again something that can be identified by a certified arborist, and this is the area you need to think about for protection during construction. Diagram on the right, one way to figure out a tree root protection zone. There used to be some real simple numbers. It's the drip line, or you measure some distance from the trunk, but it's more complicated than that, and it has to do with tree species as well as the other conditions around the tree. It's a good idea to call in an arborist to determine that protection zone. Protection barriers, these are, for protecting during construction, chain link fence, plywood. There's lots of different configurations of fencing. The fines and penalties. Use an arborist for determining these distances. Obviously, you have to account for working space, and this is where it gets tough. You got a lot of activity around the trees. You have to get strategic on what kind of movement, who's going to be moving what equipment through there, and how are you best going to protect. If it has to access that tree root protection zone, you're going to have to put down some pretty robust protection if you're moving equipment across there. So this is just a listing of construction impacts, the activity, the impact, and the method to minimize those. It's there for you to look through and ideas for protecting your trees during construction. Two of those tables I should mention just briefly is utilities. You are going to be, maybe faced with installing utilities. If you're going to preserve certain trees, you might be moving utilities under those trees or installing them under the trees. You have to bring in an arborist in that case. And there are tools for boring through the root zone, provide you with much less impact than trying to trench. So soil depth and volume, great diagram, and sort of shows you where the size, the relation of roots compared to the canopy, and you can see in this case the roots extending far beyond the drip line or the outside edge of the branches of the tree. And often the drip line is used as, that's the area you need to protect. Again, it depends on the species and other conditions, but those roots can extend far beyond that drip line. And those transport routes are located very shallow. Some soil depth and volume. Some recommendations, again, from Urban and others. Lindsay and Busek is another great source for tree management. For lawn areas, 30 to 48 inches deep, extended for 10-foot radius around that tree. In a tree, park, open space area, that might be very attainable. In a more dense urban setting, that is a lot. There are two primary soil recommendations out there that you'll see, one from James Urban and one from Lindsay and Busek from Cornell. But you'll see from Urban, 0.38 cubic meters soil per 1 square meter of canopy projection. But he adds in the type of soil, loam. This is for no irrigation with 30 inches of annual rainfall. So he throws in a little bit more detail on his soil recommendation than Lindsay and Busek. That adds a fair amount of soil volume. And then the other, a little bit simplified, 0.24 cubic meters per 1 square meter canopy projection. So you're likely going to be talking with arborists and your landscape architect about this, but these are some of the prevalent recommendations. Again, the bottom line here is this is quite a bit of soil volume, more than we usually provide for trees. Structural soils require volume for structural component, and there's less available soil. The structural soil is rock, say about this size, with a polymer and soil coating that rock. Okay, so the rock provides the structure, right? You can put that in a hole, put something over it, porous asphalt or pavers or something like that, and use that as a structural support. But what you end up with is, because it's rock with some soil around the rock, quite a bit less available soil for rooting of that tree. So structural soil has approximately 20% available soil So of that whole volume that you've installed in that hole, only about 20% is going to be actual available soil for nutrient exchange and potentially water exchange with that tree, or water uptake. Integrating stormwater management with your tree growth. Here's a picture shot we saw earlier of the silvicels going in. That's the finished product, and then a section drawing. And what you see here is actually a narrow bioretention area. The sidewalk is permeable pavers. And you can see in the section drawing that underneath that sidewalk is the silvicel installation. And that's filled with soil. There's some other things there. There's some gravel. Basically, that silvicel system provides a tremendous amount of additional soil volume for water storage as well as rooting for the tree. A great system. They're not cheap, but it's a very effective system where you can get both a structural component, stormwater storage, and healthy trees. And then this is a section of a structural soil installation. And you can see in the picture, so the parking lot, and then the shiny part is conventional impervious asphalt. And then you see the kind of duller, dark parking stalls, that's porous asphalt. And underneath that porous asphalt is the structural soil. You can barely see the trees. They're newly planted, but you see the yellow hoops next to those parking stalls. Those are barriers for the trees. So this is an example of the structural soil, crushed aggregate, 3/4 inch and a half, and fine-grained soil and polymer coating that rock. Good porosity, high permeability, load-bearing, lower soil availability. That's the drawback to that system, and it's proprietary. There's another structural approach that's not proprietary, and it's a sand-based structural soil, and it's very simple. So this is a section drawing, medium to coarse, uniformly graded sand with compost. Uniformly graded means generally the stuff's about the same size. What does that mean for permeability? High permeability. So uniformly graded sand, it's going to be generally the same size particle. It's going to drain fairly rapidly because of that. If it's sand, 2 to 3% by volume with 2 to 4 inches of saturated hydraulic connectivity typical. So that's probably because with the compost, that's going to maybe slow it down a little bit, but that I would be surprised if it would be higher than that. Typically 30 inches deep, non-proprietary. But you can see the crushed stone underneath the concrete with the sand-based structural soil. They have about 30 inches there. East Coast consultant developed this. But it's, and there's more information in the LID manual on this product. But pretty straightforward. Easy to attain materials and effective. Been used quite a bit. Not so much in this area. So just a couple of other ideas about growing healthy trees in these tight environments. Root paths, and James Urban's book describes these in detail, but these are for guiding roots to other soil volume. You might be directing roots to other tree planting areas or other open space, but they're not really so much for increasing the soil volume in those root paths themselves as allowing roots to access other areas. As opposed to root trenches, which can guide roots out to other areas, but also providing additional soil volume. And again, Urban's book provides good guidance on these, pretty straightforward. The root trenches, however, there's a structural component of that. They're larger, so if you have a sidewalk over those, you need to consider the structural stability of those, and that usually includes a layer of gravel and then maybe some reinforcement in that concrete over that trench. Just a little bit on tree performance, just to finish up. And we've been talking about, well, you're getting tree credit for stormwater management. We're going to try to grow healthy trees in these tight environments. Well, does it really work? Is this worth it? This is a really fuzzy picture, but it's the best picture I could find of Zhao's work down at UC Davis. Obviously, Davis is a different climate, really more Mediterranean. So UC Davis is down by Sacramento. Zhao built this whole thing around these trees to catch water from different parts of the tree. Very elaborate. So I think it's worth looking at, even though it's a different climate. But what he found for deciduous trees, 15% annual precipitation intercepted and evaporated. Evergreen, 27%. Their storm patterns are quite different. You can get less frequent, but larger storms. A study that's more applicable for us is Acadian in Vancouver, BC, so just up the road. And this was done actually in the urban environment, trees that were in the city. And they set up an elaborate, actually not as elaborate as ours, but an elaborate set of troughs to collect water under these trees. And they looked primarily at evergreens. That was good. 7 events. Interception and evaporation ranged from 17 to 89%. Whew, that's high. That's really high. I wouldn't use that number. That's, I think, optimistic. But the authors noted that the 89% may be due to increased temperatures in the urban environment. Intuitively makes sense. So I hope everybody understands that for us, interception of the precipitation in a conifer canopy and then the evaporation is not so much driven by solar evaporation. It's more advective, air, wind blowing through the canopy and evaporating that water. And evergreens are really effective at that, right? I mean, they said all these needles, they're like radiators, you know, getting that moisture out in the wind. This 89%, you know, could be, because that temperature would be part of that. Temp and air currents moving through the canopy. That gives you a sense of some of the numbers that we've been basing these recommendations on. Space for roots to grow, to bring in the nutrients and water. And Bartens did some really interesting research where they looked at 2 different types of trees, black oak, red maple, so this is another part of the country. And then they put these trees in different in buckets with different soil densities. And generally, the thinking is from 1.6 grams per cubic centimeter up is a point where plant roots have a very difficult time penetrating that soil. They had some bulk densities ranging from 1.3 on up to that 1.6 threshold, and then measured the infiltration rates of that soil. 63% higher in the lower compaction soil, so that's the soil, the 1.3 grams per cubic centimeter. 63% increase, that's pretty darn good. 153% higher in the higher compaction soil compared to control with no plants. Well, that's weird. How infiltration rates went up more in the higher compaction soil? Why is that? So the bottom line message here is that trees, as with other plants, can improve soil structure and infiltration rates. So another reason why emphasis on vegetation and trees in an urban environment.